One of the observations confounding atomic scientists in the early 20th century was that an electrically excited element emits light that has a spectrum consisting of discrete lines rather than a continuum of wavelengths. For this to happen, the energy of the element's atoms must be able to change by discrete amounts. Let's see how spectral lines in the visible region of the electromagnetic spectrum arise for the simplest atom, hydrogen. In this thin vertical tube, hydrogen gas has been excited by an electric current. The molecules split into separate H atoms, which absorb electrical energy and then emit light. The spectroscope separates this light into individual wavelengths, which appear as lines in the spectrum. Look through the eyepiece to see the 4 major lines in the visible spectrum of atomic hydrogen. Now we'll explore how they arise. This small bright sphere represents the ground state hydrogen atom. In this most stable state, the atom is in the n equals 1 energy level, and its single electron occupies the 1s orbital. When the atom is excited, and depending on the amount of energy it absorbs, the electron can occupy one of several higher energy orbitals, such as the 2s orbital, the 2p, the 3s, the 3p, the 3d, and so forth. For example, here, a ground state H atom in the gas discharge tube absorbs enough electrical energy for the 1s electron to occupy the 2p orbital. And then, before it emits that energy as light, it absorbs even more energy, and the electron occupies the 4s orbital. Whenever the excited H atom drops to the n equals 2 level, it emits a photon with one of 4 specific wavelengths in the visible range. To see how the 4 spectral lines appear, we'll look at some of the possible transitions from higher energy s orbitals, whose boundaries are indicated by the dashed circles, to the 2p orbital in the center. Many other transitions can occur as well. Now, as the film strip unfolds, watch these photons emerge. The lowest energy transition is from the 3s to the n equals 2 level, and the emission is a photon of red light, which has the longest wavelength. More energy is emitted with the transition from the 4s to the 2p, and it appears as a photon of green light. A still higher energy transition occurs from the 5s to the 2p, and the emission is a photon of blue light. And the highest energy transition occurs from the 6s to the 2p, which appears as a photon of violet light, whose wavelength is the shortest. Lines in other regions of the hydrogen spectrum arise when the excited atom undergoes transitions to other final energy levels. Thus, the ultraviolet lines arise from transitions to the n equals 1 level, and infrared lines from transitions to the n equals 3 level. Only an atom whose energy is quantized, that is, exists in certain discrete amounts, can give rise to spectral lines.